Thanks very much. And indeed, I'm very excited to be giving a talk at this Strings in Seoul, even though I'm in Paris. Thank you again for letting me give the talk remotely. And so the title is ADS3 RMT2 Duality. It's named after a paper of the same title with my student, Gabriele Di Ubaldo, who will be applying this cycle for his first postdoc. And there were a few other titles I was tossing around in my head, so I figured I'd just not stop at one title slide. So here are some of the others that were in consideration. A 2D CFT trace formula, defining random matrix universality in microscopic 2D CFTs, factorizing the Cutler-Jensen wormhole, and the black hole microstate spectrum of ADS3 gravity. This talk will touch on all these subjects. That'll essentially form an outline for the talk. So let me introduce these concepts from the beginning. As we all know at this point, JT gravity is believed to be dual to an ensemble of random matrices. This was established in this nice work by Saad Shanker and Stanford and built upon and contributed to by many people. Now, the JT-RMT duality, as I'll call it, has wormholes, but there's no factorization problem. What is the factorization problem? It's basically the idea that when we have multiple boundary spacetimes with ADS asymptotics, there are solutions that have a connected interior, which seem to correlate the boundaries, say the boundary partition functions, in a way which conflicts with the expectation that they should manifestly factorize. But in this duality, there is no problem because the boundary is believed to be an ensemble where some averaging over the ensemble takes place, and this can explicitly solve or just eliminate the problem in the first place. But it raises questions in higher dimensions. The way I see it, there are two main questions. The first is microscopic ADS CFT works. How do we interpret space-time wormholes given that? And the second question is the microstates of black holes should in some appropriate sense exhibit random matrix statistics. Evidence for this comes from various directions, which we'll review soon. But the question is, in what sense should that be true? And on the boundary side, in a CFT in greater than or equal to 2 dimensions, how should we, quote unquote, find these random matrices? What does it mean for a CFT to exhibit random matrix behavior, given the many other constraints CFTs must obey? In the world of quantum systems, the idea of random matrix universality is that the energy levels of a quantum chaotic system are distributed like those of a random matrix. So here I've shown this canonical plot for the spectral form factor of, say, the GUE ensemble of random matrices. I believe I lifted this from a Saad Shanker Stanford paper. Apologies for the lack of attribution. But it's a plot we're all familiar with this famous dip ramp plateau structure of the spectral form factor, which is this analytically continued product of partition functions to Lorentzian time. And so the RMT universality statement is that there should be this linear ramp at sufficiently late times with a particular slope or coefficient specifying the RMT ensemble class. So the question is, how does CFT contain or generalize RMT in a way compatible with field theory constraints, say things like constraints that define axiomatically a CFT? There are only heuristic definitions of what chaotic CFT even should mean, but we expect that a generic point in the space of CFT should exhibit some form of this universality, because a generic CFT should have a sufficiently sporadic spectrum, and there should be some random matrix encoding within that. We also know that in ADS gravity, black holes behave maximally chaotically, whether we're talking about Lyapunov growth or scrambling, or various other phenomena, including the reproduction of the ramp in the spectral form factor. Some version of this is true. Okay, so we want to make this precise. Today I'll focus on ADS3 CFT2, which is the next simplest setting for holography of both the near ADS2, near CFT1 correspondence. A consistent CFT2 exhibits locality and exhibits obeys rigid bootstrap and symmetry constraints. Say Virasoro symmetry and modular invariance of the torus partition function are the two main ones. And if there's supersymmetry, then there's a superconformal algebra, and there may be other symmetries in the game, W algebra symmetries, but this is the simplest setting that any 2D CFT has. And so the question we're used to thinking about for the past 10, 15 years is how does SL2Z constrain the heavy spectrum of a CFT on average? Something like the Cardy formula for the density of states as you go to asymptotically large dimension gives you a smooth asymptotic for the density. And Tauberian methods can improve this, and the modular bootstrap asks how modularity bounds the dimension of the lightest state, and so on. But there's a new question that these other concepts in the previous slides raises, which is that how does SL2Z constrain the heavy spectral correlations, the fine structure of this heavy spectrum? And so this gets into the world of chaos and random matrix dynamics. Something we're probably all familiar with from recent work in the subject is that semi-classical gravity computes coarse-grained observables. Okay, so what it even means to do a computation that sees this random matrix nature of a dual CFT2 is not immediately obvious. Most recent work in ADS3 studies saddles of fixed topology, like those shown here, which are governed by ETH matrix elements. So all four of these two boundary wormholes in ADS3 are fixed by OPE asymptotics, which themselves are fixed by crossing and the low energy data of the theory. And there's been a very nice set of papers studying wormholes like this and interpreting them in CFT terms, in terms of some probability distributions of CFT data that encode this ETH asymptotic of the spectrum. But they're not sensitive to the randomness or the chaos of the black hole Hilbert space. They're not purely spectral quantities. They always involve OPE data, which can be argued to take a certain form. But I think it's clear that to know whether, say, ADS3 pure gravity exists, we need to do the full path integral over metrics, and we must reckon with this random matrix nature of the black hole Hilbert space. Okay, so that's the philosophy of today's talk, and so we're going to try to attack this. Now, there's a calculation to try to understand here, which is that of Kotler and Jensen, who computed the two-boundary torus wormhole in ADS3 pure gravity. So there are two boundary tori. They are connected by spacetime in the interior. I'll call this amplitude ZCJ. It depends on two modular parameters, tau1 for this boundary torus and tau2 for this one. And it's a fully SL2Z times SL2Z invariant quantity. Now, this is a bit mysterious. First of all, it's not a saddle point of the bulk path integral. They had to compute it by other less familiar methods, but compute it they did. Given that, though, there's no CFT computation of the same quantity, but it seems to indicate something like a spectral level repulsion. For example, they extracted from it a linear ramp in the spectral form factor. But the linear ramp of what exactly is the question. And it's suggestive of some concept of random CFT, which is a name that they gave to denote this collection of ideas that I've tried to allude to. So microcanonically, this is computing something like a two-level spectral correlation of a chaotic CFT. But first of all, it's not really clear what boundary partition function type quantity this is correlating. It's not clear what the brackets here should mean. All of which is to say that we don't know what random CFT really is as a quantitative concept. So today I'll present a framework for understanding random matrix dynamics in 2D CFTs. And if we apply it to the putative CFT dual to ADS3 pure gravity, we'll be able to give a microscopic explanation of this Kotler-Jensen wormhole. The lesson is that random matrix behavior can emerge dynamically from chaos in an individual CFT once we process the symmetries and think about the problem in the right way. And I want to emphasize that I'm not working in a model of 2D CFTs. This is with the bona fide ingredients of a specific well-behaved CFT. Okay. So let me say in pictures what's going to happen with respect to the Kotler-Jensen wormhole, then we'll dive in. Okay, so the idea is here's the Kotler-Jensen wormhole, and we'd like to understand what microscopic quantity it might be computing something about. So here we have represented the wormhole as some sort of gluing of two one-boundary quantities. And so we'll show that there's a way in which you can coarse grain a piece of the partition function that contains the chaotic states to generate a wormhole. And in reverse, you can factorize a wormhole to extract this chaotic data from a CFT. Now, applied to the pure gravity setting, this will allow us to go back and forth between the Kotler-Jensen wormhole on the one hand, and a quantity we'll call ZRMT on the other, which encodes the quantum substructure of the black hole microstate spectrum of ADS3 pure gravity. And the fact that we're able to do this is somewhat remarkable and relies heavily on processing modular invariance correctly. Okay, so the outline for the rest of the talk is that first I will present a 2D CFT trace formula, which is rooted in this approach to modularity. This will help us define some random matrix universality in microscopic 2D CFTs, so we'll come up with a necessary and sufficient condition for a theory to exhibit a linear ramp in the spectral form factor. And then we'll turn to wormholes in gravity, the Kotler-Jensen wormhole in particular, which we will factorize in the way I just described, and that will spit out for us this fine-grained information about the black hole microstates of ADS3 gravity. So that's the plan. Okay, so the first goal is that we want to isolate the chaotic spectrum in a way that respects modular invariance. Now, already there's a challenge because, as I alluded to before, there's no obvious sharp notion of what the chaotic part of a 2D CFT spectrum is. Now, when we think about modular kernels on the CFT side or the holography of ADS3 black holes and handle bodies on the bulk side, those both suggest a natural definition, which we'll get to in a moment. Now, as for the modular invariance, as we know, its power is the ability to relate UV data, high energy data, to IR data, that is the low-lying spectrum. Now, normally the modularity of a partition function is obscured while we choose to manifest the character expansion. But there's a way to think about the partition function which naturally incorporates both of these aspects and sort of sews them together. Given a primary partition function of a Virasoro CFT, by that I mean no extra currents that are conserved, with C greater than 1, we can write it as a sum of two manifestly modular invariant pieces. So before getting into this, let me just point out a few definitions. The primary partition function is just the ordinary torus partition function multiplied by a factor, which preserves modularity but strips away the Virasoro descendants of all the primaries. So I'm going to call this ZP. And throughout the talk, tau is x plus iy. In particular, y will appear sometimes. That's im tau. And this variable c is defined as c minus 1 over 24. Okay. So we can formally write this partition function as a sum of this z hat light plus what I'm calling z spec. So what are these two pieces? Z hat light is the sum over all of the light states plus their modular completion. So first, you imagine taking your spectrum, summing over all states where h and h bar are bounded above by c minus 1 over 24, or h bar rather. That distinction is actually important for chaos. I can say more about that if anyone would like. And you sum over these states, okay? So you have a bunch of states that satisfy this condition. And then you can modular complete this. That's not a unique concept, but it can be done. It probably needs to be regularized. This is familiar for people who study Poincare sums. And that defines this modular invariant quantity z hat light, which is something like, for example, a Poincare sum over z light. Okay. Again, I stress this is not unique, but that won't be important for what I say today. Think of this as the light spectrum plus the contribution of those light states to the heavy spectrum as required by crossing or modular invariance. So given your partition function, you subtract all that stuff out, and what you're left with is something we call z spec, for reasons that'll become clear in a moment. I want you to think of this as the chaotic partition function. It has support only on states where h and h bar are greater than or equal to xi. And in gravity, this is the regime in which black holes live. All black hole states satisfy this condition. Just to stress, I'm not restricting to large C here, but it's useful for intuition to point that out. And this quantity z spec is square integrable on the fundamental domain of SL2z.
Can you say something? Yeah, can I ask a question?
Yes.
Yeah. If you back up a slide.
Yeah.
So I'm confused about what do you mean by light states plus modular completion? So, I'm trying to formulate this. So if I take, say, the identity, its modular completion is what?
Its modular completion would be, think of it as the Cardy formula, the non-perturbative version of Cardy. So in particular, if I modular complete by Poincare sum, modular completion of the identity is exactly this Maloney-Witten-Keller partition function.
Okay, so isn't that accounting for all of the high energy black hole states?
It's a smooth approximation to them. So, right, I mean, as you know, that partition function itself is not unitary, first of all. So it's not
right.
counting black hole states of a would-be unitary theory. But I want you to think of that as a smooth approximation to the exact spectrum of some underlying theory. And
so then does that mean Z spec is something like fluctuations around that asymptotic formula?
Yes, and I'll show a figure that shows exactly that in just a moment.
Yeah. Okay, thank you.
Sure. In fact, let me just jump ahead. Don't look at these slides. Don't look. All right, there we go. Wait, that was risky. This figure. Okay, so we'll come back to that. All right, close your eyes. Okay, good. All right, so this looks like an average of some kind, as Emily and I were just alluding to. It subtracts the light states and their rangers under crossing. And the idea of this piece as an average can be made concrete in the context of Narain CFTs. If one averages over the full Narain moduli space with the Zamolodchikov measure, the average of this piece over moduli is 0. So this piece is literally the sort of average, the piece that the full average equals, right? It's the self-averaging piece. And so it's plausible that some form of this notion persists in Virasoro CFT, but the challenge is, of course, there are no moduli there, so one has to define what one means by average. Now, let's understand Z-spec a little bit better. Z-spec is square integrable in the fundamental domain of SL2Z, and any such function admits a unique decomposition into an SL2Z invariant complete eigenbasis of the hyperbolic Laplacian. There are 3 components of this L2 space, which we'll talk about in turn. Not in too much detail, and perhaps you've seen a talk by me in the past couple of years where I've gone over this in a bit more detail, but I'd like to just present it so we know what functions we're talking about. The first piece is a constant. The second piece are Eisenstein series in the so-called critical line. And the third piece are these Moss cusp forms, an infinite discrete tower of eigenfunctions which satisfy this Laplace equation. Okay. I'll say slightly more about these, but for our Z spec, it admits a decomposition into 1, 2, 3 pieces with spectral overlaps determined by the Peterson inner product, or in this case, since I'm using the so-called completed Eisenstein series, which is just some rescaling by a completed Riemann zeta function, I've denoted the overlap with a bracket to indicate that there's some division by some factor. Okay. And this integral here is over the critical line. Okay, so for this talk, the modular average actually is not so important. You can shift it into Z hat light just by adding it there and subtracting it here. In other contexts, it's very important, but not so much today. The second piece, which is more important for today, is the Eisenstein series. The Fourier decomposition of the completed Eisenstein series we write like so. So the functional form is very simple. It's just these modified Bessel functions. J is the space-time spin, so think of this as a spin decomposition in 2D CFT language. And the Fourier coefficients are these nice number theoretic objects. The 0 mode is just the J goes to 0 limit of this, which ends up just being a sum of 2 power terms. And this lambda is this completed Riemann zeta function. The Moss cusp forms have a very similar structure, save for a few important differences. The first is the Fourier coefficients, which I've called B, as opposed to A for the Eisenstein series. And the spectral parameters themselves are not actually known analytically, even in a single case, but a lot is known about them numerically and asymptotically. And there's no 0 mode. Okay, and so as a result, these things decay exponentially at the cusp and in mean. So schematically, here's a picture of these objects. You should think of the Eisensteins as smooth functions and the cusp forms as chaotic functions, as a plot of the squares projected onto the zero mode sort of heuristically shows. Here, I'm showing you a density plot of two different mass cusp forms at different values of the spectral parameters where they exist. And you can see the plots, okay, they have some similarities, but it differs quite a bit. And in particular, if you look at where the global maxima and minima are, they're in what we physicists might call somewhat random places. They're not down here at the corner, and they change wildly as you change the spectral parameter. This is some indication of the chaos of these mass cusp forms. And indeed, there's a very rich story of arithmetic chaos surrounding these objects the mathematicians still intensively study. In a recent paper by Hale, Reeves, and Rosalia, they gave a nice exposition of these properties in the CFT2 context. I would recommend that. This, for example, is a match of the actual mass cusp form data against some asymptotic Wigner semicircle-like distribution that these Fourier coefficients are conjectured to obey. Okay, so that should suffice as an introduction to those functions. So here's the slide from before. So we want to return to this question now. Okay. Now to pursue the idea, the key for today will be to study the primary density of states instead of the partition function. Now here we are back at this slide. So microcanonically, the density of states at spin j can be split likewise into this rho hat light piece and rho spec. Okay. And here's how to think about this. So the exact density would be rho. Okay. So this is the exact primary density of some theory. I'm approximating it here as a smooth curve, thinking, for example, about some c goes to infinity limit. But really, this is some smooth curve that is approximating some sum over delta functions. Okay. Now, rho hat light is some continuous asymptotic, which behaves exponentially. That's this dotted line. So it's some smooth curve here represented by the square root edge of the Cardy formula starting at t equals 0. And rho spec are the oscillations in between. Okay. So they capture the difference between these two things. And this thing must oscillate very strongly in order that rho has the fine structure that it needs to in order to actually be the original density, because rho hat light is this smooth exponential thing. So in particular, rho spec oscillates on scales delta t, where t is this reduced twist parameter, as it's called, which are like of the order the inverse mean level spacing, something like e to the minus s card. Okay. So here's the picture for what rho spec is computing. It's computing these little fluctuations between the real density and this asymptotic approximation to it in the chaotic regime. This hints at some analogy with the Gutzwiller trace formula for quantum systems. The trace formula takes the density of a quantum chaotic system, the density of energy levels, and writes it as a mean density plus some oscillatory piece. And what the trace formula then does is to write this oscillatory piece as a sum over periodic orbits labeled by gamma. The sum takes the following form. There's an e to the I times action. This is multiplied by the period, which is given by the derivative of the action. And there's a one loop determinant kind of piece, which in general can depend on energies, but just think of this as some prefactor. Okay. Now, this is something that holds in the semi-classical regime of energy levels for some quantum chaotic system, but when the formula applies, it takes this form. So there's a suggested analogy with what I just showed you. The analogy that this suggests is that the mean energy density maps to this rho hat light, this smooth approximation to the chaotic spectrum, while the oscillatory piece looks something like rho spec for any fixed spin j. And of course, you already noticed, right, in the quantum system setting, there's no j. So this is one of the differences between 2D CFTs and quantum systems. Right? Now, it turns out that this analogy is realized precisely by this SL2Z spectral decomposition on the nose. So in the SL2Z spectral basis, this rho spec density is a sum over the eigenbasis elements. And if you compute the eigenbasis elements in the microcanonical ensemble, you find that they take exactly the form of individual periodic orbits. What do I mean by that? That this basis element rho, where this here represents either rho star or rho n, is exactly this one. The action is
Eric, you're breaking apart. Can you hear me?
Spectral,
We cannot hear you. No, I can't hear you still. Wait, why don't you disconnect and reconnect again? There's no keyboard here. 비디오 송출. Eric, could you just switch off your video for a moment? Hello.
Yes.
Eric, somebody should type.
Yes.
Do you hear me?
I do.
Okay, now you're back. So couldn't hear you for the past 2-3 minutes. So can you go back to your previous slide and repeat?
Yes. Yes. Here?
No, one.
Here?
Yeah, there.
Oh, wow. Okay. Sorry. Yeah, that's not good. Okay, sorry about that. Sure. So this being a key point, let's reiterate it. If you take the spectral density and write it in this basis, you find that the eigenbasis elements take exactly the form of a periodic orbit as in the Gutzwiller trace formula. So taking this rho to stand for either the Eisenstein piece or the cusp form piece, it takes exactly this form. So, so these are just obtained by doing an inverse Laplace transform of the basis elements in the canonical, the Eisenstein series, and the cusp forms at spin j. And it takes exactly this form, e to the I action times period times coefficient, where the C stands for the Fourier coefficient either of the Eisenstein or the cusp form. These identifications follow uniquely if we demand that the action is real and that the j goes to 0 limit gives you the correct answer. So the correspondence between eigenbasis elements and periodic orbits is very clean, and this gives us a hint about what to do next. A key fact for later that Gutzwiller does not have, in general, is that this 2D CFT trace formula expands over a complete eigenbasis. We'll return to that later. Can you still hear me?
Yes, we are good.
Thank you. Good. Okay. So this answers our earlier question of whether z hat light can be thought of as an average. It can. And it also immediately gives us a path to establishing random matrix universality in 2D CFTs. So what is that path? Well, we just mimic what you do with the Gutzwiller trace formula in quantum systems. what do you do there? You discover the linear ramp there by taking a product of two densities and restricting to the diagonal of the double sum over orbits. By diagonal, I mean you restrict to those orbits with equal and opposite actions. This is known as Berry's diagonal approximation. So here we have our own trace formula that looks exactly like the Gutzwiller trace formula. So we should do the same thing. We should consider a two-level correlation and understand what it means to do the diagonal approximation, and then ask what is the underlying condition on the spectral density, namely the overlap, to produce a linear ramp.
So can I ask a question?
Yeah.
So talking about periodic orbits, in ordinary chaos in the Gutzwiller trace formula, the periodic orbits are depend on what system you're talking about. So where is that data being put in here?
Yeah, it's sort of popping out. So there's some universality in that data for 2D CFTs. What differs is the density of orbits, that is the spectral overlaps, but the basis of orbits is universal.
Okay.
Yeah, indeed. I mean, that's closely related to this point, which will end up being very non-trivial because, right, perhaps you can already see, it's an expansion over a complete eigenbasis of periodic orbits. So that means that if you have something like a two-level correlation, you can undo it, right? You can factorize it because you can read off from, say, all you need to know is the density of those orbits, and then the coefficient, and you can read off the action. You can read off the entire thing that you square to get your product. But we'll get to that later. Okay, so what is the diagonal approximation in 2D CFT? Well, we'd like to understand this from a bottom-up point of view, not just to posit it. So if you coarse grain by smearing over a window and twist, then you first of all show what we sort of already said before. First, if you do this for a single copy of the density, the basis elements coarse grain to 0. If you take a product and you coarse grain over some, you take a product of densities defined at different twists, but with the same spin, and you fix the mean twist, and then you average over mean twist, average over a small fluctuation around that, then you find that this is non-zero only when the spectral parameters are equal. So the CFT avatar of the diagonal approximation sets the spectral parameters equal in a product of densities. That makes sense because the spectral parameters are labeling the orbits. Right? So in the canonical ensemble, we can rigorously define something we call the diagonal partition function, which pairs eigenvalues of the hyperbolic Laplacian. So you take your z spec, you square it, so you take two of them, and you project onto the kernel of the difference of hyperbolic Laplacians. So what this does is, in the spectral language, it correlates and pairs the eigenvalues. So in spectral space, this thing has the following decomposition. Instead of two individual sums over the basis, you have one. You've taken the diagonal projection. You pair the Eisenstein series, you pair the cusp forms, and there are some nagging cross terms because cusp forms and Eisenstein series are actually degenerate. This is perhaps, for some, a technical slide, but for others, an interesting slide. The technical can also be interesting, so perhaps that works out for everybody. This fact that the Eisenstein series and the cusp forms are degenerate, that is to say, for every cusp form, they sit on the critical line of eigenvalues. So there's always an Eisenstein series sitting at the same place. So if you pair eigenvalues, then there actually are cross terms that pair different orbits, right? These two functions have different Fourier coefficients. So from the Gutzwiller point of view, these are different orbits. So instead of projecting onto differences of the Laplacian to pair eigenvalues, we should really define our coarse graining as pairing eigenfunctions. This can be done by doing what we call a Hecke projection. So to find something we call Z Hecke, it doesn't have the cross terms, it's diagonal in spectral space. And this is defined formally by taking your product of two partition functions and projecting onto this kernel of the difference of Hecke operators at every spin j. I don't need to introduce the full definition for what Hecke operators are, suffice it to say that when you act with them on the basis elements, the Eisenstein series and the cusp forms, you get the spin J Fourier coefficient out, here with some factor of 2 for Mark had mentioned. Okay. So when you act on a cross term, an Eisenstein times a cusp form, you get the difference of the Fourier coefficients, and the Fourier coefficients are different from each other. So this is non-zero. So when we project onto the kernel, we kill the cross terms. Okay. You should think of this as an enhanced coarse graining that pairs eigenfunctions, which is very natural from the periodic orbit point of view. Okay, so we're going to call this thing Z Hecke. It's like a Z diagonal that accounts for this quirk of life on the fundamental domain of SL2Z, that there is some degeneracy in the eigenfunctions. Okay, so now the random matrix universality. So once we get our heads on straight, this will all pop out very, very smoothly, I think. So for simplicity, we're going to take, so first some of these formulas are written in terms of Z diag. Z diag and Z Hecke, if you project to the 0, 0 Fourier components, they are the same because the cusp forms, recall, have no scalar component. So the cross terms will just vanish. Okay, so all these formulas here, when I look at the scalar Fourier mode, you can think of this as Z Hecke or Z diag, doesn't matter. So this takes the form, we just take our formula, we expand, we write the Eisenstein 0 mode, we plug it in, and we just ask what pops out. It just takes this form. It's determined in terms of some function R of Z, which is just the inverse Mellin transform of the square of the spectral overlap. Okay. So remember, we start with a chaotic CFT. We form Z spec by subtracting out the light stuff and its modular completion. That uniquely specifies this overlap given a modular completion. And so then we can construct this 2-copy partition function. And we're looking at the scalar mode, where here R and Z are defined in terms of im tau 1 and im tau 2, like so. Okay. To probe random matrix universality, we want to go to low temperatures. That's a limit of large R and Z fixed. Okay, this is the so-called near extremal limit. There are different kinematic regimes we might be interested in, namely 2 of them. The first is the Euclidean regime, I would call it, where y1 and y2 are real, and then z is real and positive, and that's this green line here. It extends down to 0, but this region here is just a reflection of this region. So we call this the low temperature contour. If you want to study the spectral form factor, as you know, you take these inverse temperatures to Lorentzian signature in this way. And then if we define z as e to the I theta for some angle theta, as you increase the ratio tau t over beta, where t is Lorentzian time, you sort of move from 1 along this unit circle out to the late time point at -1 here. Okay. We call this the spectral form factor contour. All right. So these are the different kinematic regimes in which we're interested in this object. All right. Now, to establish random matrix universality, we want to study the spectral form factor and ask, what does Z spec need to do in order to get a linear ramp? The spectral form factor, just to define it, we define this as k beta of tau, is the product of primary partition functions with this configuration of temperatures, where we divide by this factor to strip off something that we use to define the primary partition function. This is just here such that at late times, a linear ramp means linear, not quadratic. Okay, so that's what this pre-factor is doing. The key point is that Z primary, full primary
Eric, you're breaking apart again. Hello. Hello. Do you hear me? You're frozen again. Can you briefly switch off the video to see if that works? Hello. Same. Eh, Eric, do you think you can log out and log in again? Disconnect and reconnect?
Okay. That's the state. Topically flat. So as you go out to larger here. So this is the main result about random matrix universality in 2D
Oh,
CFT.
now you're back. Sorry. So same thing happened again. So you've been disconnected for like past 2 minutes or so.
Was I here?
Can you go back to previous slide?
Here.
No. Next one?
Here.
No, next. Not this one.
Do you mean forward or backward?
Next slide. Yeah, here.
Okay. Thanks.
Maybe it helps to switch off your video for a while because maybe there's a bandwidth problem.
Sure, it's that is possible.
Yeah, let's try that for a while.
Mm-hmm. 1 second. Sorry. Let me just. Oops. All right. Okay. With my video off. Is that good?
Yeah. Thank you.
Right.
Let's proceed then.
If it keeps happening, we'll turn off the audio too. You know?
That's not going to work.
Okay. So sorry for these issues. I wish I knew what was going on. In any case, so the spectral form factor, let's define it. It's the product of primary partition functions with these Lorentzian kinematics, with some coarse graining denoted by these brackets, and I've divided just by a factor which is related to the use of the primary partition function. When there's a linear ramp, this thing will behave linearly after we divide by this thing. Okay, so that's just a prefactor for convention. Now, the key point is that Z primary and Z spec differ only by dip terms. This is a bad typo. This should say dip, not ramp. This might be familiar to you from gravity. Well, the light states and their modular completions are these classical contributions, which give you this initial classical decay. That's what this dip is. Okay. So given that, the spectral formalism I've introduced is tailor-made to study the spectral form factor at late times, right? We replace this by Z spec, and we've defined exactly an object, Z diagonal, or Z hecke, whose job in life is to be a coarse-grained product of two partition functions restricted to the chaotic part of the spectrum. And so in this diagonal regime, we should exactly reproduce the ramp from this object I've introduced. Okay. So now we can easily impose the ramp on Z diagonal and translate this into a statement about the CFT data. So the linear ramp with the right coefficient is given here. And if we translate this into this function R, which we introduced in the previous slide, as the inverse Mellin transform of the squared overlap, that just implies that R has to have a simple pole as Z approaches -1, which was this late time region down here. Since R itself is constructed from the underlying microscopic CFT data, this is equivalent to a condition on the overlap, that is on Z spec itself. Translating this pole into a spectral statement, you arrive at the statement that the squared overlap, as you go to large spectral parameter omega, must decay asymptotically exponentially, times some function which can oscillate as you go out to large omega, but approaches a constant, this constant C RMT, at infinity. Just checking, you can still hear me, is that correct?
Yes, we're good.
Okay, good, thanks. And so that's the main result about random matrix universality. We've translated the presence of a linear ramp in this coarse-grained spectral form factor into a statement about the original chaotic CFT data that we coarse-grained in the first place. Now it's phrased as a statement about the Z spec, which is explicitly parameterizing the chaotic part of the spectrum. It would be nice to translate this into a statement about the low-lying data. That would be a very interesting thing to do in the future. But for now, this is a necessary and sufficient condition for a ramp, phrased in terms of the spectral part of the partition function. Okay. For context, note that convergence of the spectral decomposition only requires that there's a power law fall-off. So we can say that in spectral space, random matrix universality is a statement of rapid decay at infinity. Where here rapid decay is meant in the sense of Zagier. Now, what are some notable properties of this I'd like to emphasize? The first is that it's microscopic, right? This overlap belongs to a single copy of the CFT. So we translated this statement about the ramp, which is a coarse-grained 2-copy observable, into a statement, a necessary and sufficient condition on the single microscopic CFT whose statistics we are trying to compute. It's also practical. If I have a CFT partition function, I can form Z-spec explicitly and then just check. Right. Of course, that's a statement really, to some extent in principle, the given a CFT is the hard part, but it is completely explicit once you have that. And finally, I should say there are universal corrections to this. If you take this ramp and you plug it into the other piece of what defined the 0,0 component of Z diagonal or Z hecke, then, right, there was this piece, and then there was this additive piece, which involves an integral and a sum. You can show that, right, you plug this into that, and out pops a correction. It takes explicitly this form. It's a correction because, see, it doesn't depend on Z. As Z goes to -1, it's regular. So in spectral form factor kinematics, this is subleading, but the presence of the ramp at late times implies that this component has to have this piece. Okay, remember that for later.
Sorry, Eric, can I ask you a question?
Yeah.
So these two terms, R and S, are they morally like the same as y to the S and y to the 1 minus S for the Eisenstein? Do they have the same origin?
Yes, exactly. Yes.
Okay. Thank you.
Mm-hmm. Yeah. You just start from, you plug that in, you show that one of them gives this and the other gives that. So indeed. Okay, so to recap, here's how you find the random matrices in a 2D CFT. You isolate the chaotic spectrum in a way that's consistent with modularity. You consider the 2-point correlations, coarse-grained in a way that reveals the random matrix universality. And that lands you on the Z hecke. And if you want to study the spectral form factor, you go to those kinematics, you go to late times, and then you extract from this the ramp and the necessary and sufficient condition for the ramp. This is that in words. We don't need to say that. Okay. So at this point, we're going to transition to the gravity part. Let me ask how much time I have. Maybe the technical interruptions have taken some time away. So let me just double check on that.
Yes, you can proceed.
Yeah, how much time would you say I have?
Like, okay, let's say 10, 15 minutes since we had some.
Great.
Yeah.
Thanks. Thank you. Okay, good. So now on to gravity and wormholes. Okay, so for the sake of this talk, let's define wormhole amplitudes in the following very general way. If you have a 2-boundary spacetime or a multi-boundary spacetime, as is probably familiar from the story about BTZ black holes and the black hole fairy tale in ADS3, invariance under large diffeomorphisms in semi-classical gravity gets manifest as a sum over geometries in the bulk, which manifestly implements boundary modular invariance. So SL2Z sums over some seed are associated with modular transformations on the boundary, and each term in the sum is a different contribution of a geometry to the path integral. This statement is really just a statement about large diffeos. It's not a statement about single boundary BTZ black holes. And so if we define wormholes very generally as these kinds of Poincare sums in which boundary modularity is manifest in the bulk as a sum over modular images suitably defined, this will define for us a wormhole. Okay. For a torus wormhole in particular, we can define by this definition, this should be defined as a sum over SL2Z, or perhaps with some quotient here, of some seed function f0. It's a sum over relative modular transformations. And f0 itself, in order for this to be fully modular invariant, is invariant under simultaneous modular transformations on tau1 and tau2. Wormhole amplitudes enjoy special mathematical properties. So you can show that just given a function of this form, it is Hecke symmetric. In other words, this operator Tj12, the difference of Hecke operators acting on tau1 and tau2, annihilates this thing. Okay. So this motivates, in part, the CFT introduction of Z Hecke in the first place, because wormholes in gravity have this symmetry. Okay. And to the extent that we believe them to represent coarse-grained products of partition functions, it clicks very well with a general definition of that object, okay, which I already independently tried to motivate using periodic orbits, but this gives another point of view. Okay. So more generally, what are some of the properties these wormholes have? They're Hecke symmetric. They depend only on the invariant hyperbolic distance between tau1 and tau2. And perhaps most importantly of all for today, they have a maximally simple spectral representation. Recall that Z Hecke was diagonal in the spectral basis. What you see here is that this wormhole amplitude has the same overlap function controlling the Eisenstein part and the cusp form part. In terms of CFT data, if we interpret this as a Z Hecke of some product of Z specs in a boundary CFT, some product of chaotic partition functions, then this overlap is just the square of, this overlap here is just the square of the underlying spectral overlap of the CFT. So the idea here is that we have a wormhole fairy tale. We want to interpret these modular sums.
Sorry, Eric, before you proceed, I missed the point. So why is the spectral overlap with the Eisenstein the same as the one with the cusp forms? In general, they're not the same, right?
It's something you can prove from the form of a sum like this.
Oh, I see, directly from the Poincare seed.
Correct, yeah.
I see, thank you.
Yeah, indeed. In general, Z Hecke does not have this property, but these have this yet further property that the overlaps are the same. Yeah. Okay, so if we interpret such sums as Hecke partition functions, then these overlaps are just the squared Eisenstein overlaps of the boundary chaotic partition function. Okay. Okay, so with that more general wormhole setup, let's now turn to the Kotler-Jensen torus wormhole. And I hope you'll agree that the formalism fits it perfectly. Okay. So from their paper, the wormhole, as computed using interesting constrained instant-tongue techniques, takes the following form. It's the sum of relative modular transformations of a seed, which takes this form, 1 over 2 pi squared times the inverse chordal distance, okay, which we can write like this. You can sort of ignore the details of this notation. It's a very simple seed. Now, what's the point? We interpret this as an instance of Z Hecke in a dual CFT. From their paper, we read off these R and S functions from before as follows. The R function is just 1 over pi times 1 over 1 plus Z, and S is likewise this thing. In spectral space, just translating this to spectral space by Mellin transform, it takes this very elegant form. The overlap is just a product of gamma functions, aka a 1 over cosine, 1 over sine. Okay, so by now, I hope this is striking. This term here is exactly the rent. Not just asymptotically as Z goes to -1, as random matrix universality would require, but exactly the rent. And likewise, this other term here is the universal correction that is implied by the presence of the rent, and exactly that correction with no other pieces. So in a quantitative sense, ADS3 pure gravity exhibits pure RMT statistics to the maximal extent possible. In other words, after processing the symmetries, the Cutler-Jensen wormhole saturates the exact RMT result with no further corrections. We call this max RMT, the maximal realization of random matrix universality consistent with Virasoro symmetry and modular invariance. ADS3 pure gravity exhibits max RMT statistics. In other words, the Cutler-Jensen wormhole is extremal in the space of wormhole amplitudes. You can think of this as the idea that whereas gravity is maximally chaotic at early times by way of its Lyapunov growth saturating the bound on chaos, here we're showing that it's maximally chaotic at late times in the sense of random matrix universality being maximally extended over all of parameter space. Now, a brief side comment. In some sense, these results are a little bit of a rebuke of the idea that gravity is dual to an ensemble average. They support the idea that apparent averaging can emerge from chaos of a black hole Hilbert space. And though semi-classical gravity does compute averages in the statistical sense, which is induced by the large N limit, they need not be interpreted holographically using ensembles of CFTs or approximate CFTs. So while our results for ADS3 wormholes are perfectly compatible with those interpretations, if one desires, it's very satisfying to me that the torus wormhole admits a clean microscopic interpretation in bona fide 2D CFT with no tweaking of the traditional dictionary necessary. Conversely, I would say it sheds light on the way in which this apparent averaging does emerge from chaos. And now finally, we can factorize the wormhole, and that'll be my last trick, and perhaps the most important of all for future developments. Now, here we recall this key fact, which is that the trace formula expands over a complete eigenbasis. So given your wormhole amplitude, you can factorize it, right? We have the spectral decomposition of this thing, so we can extract the overlap whose coarse-grained product gave rise to it. That's what factorize means here. And we call that one boundary quantity ZRMT. In other words, we solve this equation. And the solution is unique. It's just, in a suitable sense, the square root of the Cutler-Jensen wormhole. So ZRMT has an explicit spectral decomposition where the overlap is essentially the square root of the overlap from before, which we can write in this very interesting way involving Riemann zeta and gamma functions. So what have we learned? We know that the gravitational path integral should include the sum over smooth saddles, that is empty ADS, and all of the BTZ black holes. But now we've determined another more fine-grained piece of it explicitly, ZRMT, which encodes the leading RMT fluctuations of the black hole spectrum. So in that cartoon from before, rho gravity is the solid black line, the actual density that we want to understand. Rho Cardi is this dotted line. And rho RMT, which we've now determined explicitly, is this green bit. In view of these extremality principles I described earlier, these fluctuations of BTZ black hole microstates are as random as possible in a very specific sense, consistent with the symmetries of ADS3 gravity. So to reprise this slide, here's the general procedure for starting from some chaotic partition function and landing on this coarse-grained product. In ADS3 pure gravity, the calculation of Cutler-Jensen encourages us to interpret Z Hecke as equal to their amplitude, and then we factorize it to obtain ZRMT, which contains these fluctuations of the black hole microstate spectrum of ADS3 pure gravity. To say a few more words about this, you can think of ZRMT as an ADS3 half wormhole. What does that mean? It's a single boundary, non-self-averaging quantity, right? It's ZRMT is Z spec for pure gravity, so it averages to 0. If we glue two of them in spectral space, it makes a smooth wormhole, and the gluing is sort of done along this spectral direction, which has this very erratic behavior given by what we call the Riemann zeta phase. So we can rewrite this overlap from before, just very simple manipulations, as this factor here times a phase. This is a regular piece, not interesting. This is a chaotic piece, very interesting, which here I've plotted as a function of frequency. And so you take a product, you glue along the spectral direction, and the randomness in this half wormhole, as parameterized by the Riemann zeta function, echoes the original ADS2 half wormholes, or broken cylinders, described in these papers down here, where we're taking two objects which have this sort of erratic behavior and gluing them. Here, that gluing is done in spectral space, and we get a smooth wormhole. Now, some last words on where to go. If Cutler-Jensen were fully non-perturbative, we would have a complete proposal for the exact path integral of semi-classical gravity. But instead, it's just expected to be the first of an infinite series of off-shell contributions to this two-boundary wormhole with torus boundaries. There should be other geometries with interior topology, which should be further exponentially suppressed, but no one's computed those. So a more accurate equation would be the z gravity equals the sum of these two terms, plus some new piece, which we call delta z RMT, which naively has an expansion exponentially suppressed in C, where C is a central charge. In fact, what we've shown is that this piece must be there. Right? Not only is it expected to be there geometrically, it must be there. The proof is quick. Suppose you set that to 0. This first term, the sum over smooth saddles, is famously non-unitary, and that non-unitarity is controlled by the central charge. But ZRMT is independent of the central charge. So these extra non-perturbative terms must be there. And not only that, they must resum in some manner to lower the semi-classical black hole threshold. In other words, there's an order of limits issue. Right? ZRMT is the piece of the partition function which gives the leading order spectral correlations at large C. But if you take the large C limit first and set this delta ZRMT to 0, you get something non-unitary. Right? So there must be some resummation that happens, such that in fact there are pieces of the spectrum which are not purely in the spectral chaotic region that slightly lower the semi-classical black hole threshold. In the proposal of Maxfield and Teriaci, they give a partial perspective on how this should work. This is a paper from a few years ago where they advocate that Seifert manifolds are off-shell topologies that should be included in the 3D gravity path integral. And they motivate this by looking at near-extremal physics and dimensional reduction to JT plus defects. And it's a very elegant proposal, but it's not been explicitly realized in ADS3. And what I'm saying here is perfectly compatible with it. And it would be very nice to see to what extent this proposal fits in, to what extent the Seifert pieces fit into this sum of terms as written here. So to conclude, I'll present a bulk challenge and a boundary challenge. The bulk challenge is to derive non-perturbative RMT statistics from off-shell partition functions. That is, to go beyond Cutler-Jensen and try to complete that into something non-perturbative, where you could even imagine trying to get the plateau in the spectral form factor. And on the boundary, one would like to just construct from the bottom up a unitary partition function, which adds to these two pieces, which we now know are part of the bulk path integral, something which unitarizes it. And more generally, if we can understand how to incorporate random matrix statistics into the modular and conformal bootstraps, that would be very interesting. So let me conclude there. Thanks.